All right, so hi everyone, and welcome back to the Theory of Computing for Fairness seminar series. Today we're pretty excited to have Logan Stapleton, as our speaker. So he's going to tell us about his work on an algorithmic framework for fairness solicitation. And so Logan right now is a third-year computer science PhD student at CMU, where he's working with Stephen Wu. And so his interests lie in machine learning, in human-computer interaction, and ethics. And so he's working right now on discrimination and fairness in machine learning, on algorithmic economics, and algorithmic decision support tools used in governance. And so, yeah, take it away, Logan.
Thank you so much, Juba. And thank you for having me. I'm going to share my screen real quick. Can everybody see this? Cool. Okay, cool. Yeah, so I'm Logan Stapleton. Today I'll be presenting my paper, An Algorithmic Framework for Fairness Solicitation. And this is a joint work with Christopher Jung, Michael Kearns, Seth Neal, Aaron Roth, and Zhuwei Stephen Wu. So the motivation for this work is to involve stakeholders into the process of defining algorithmic fairness, and to do so in a way that captures stakeholders' nuanced contextual fairness beliefs. And a little outline for the talk today. First, I'll talk about more of a motivation for this general problem of fairness solicitation, and then a little bit of related work. And then second, I'll set up a computational problem that follows from this problem of fairness solicitation. Third, I'll show how to solve this computational problem. And then I'll discuss an application of our framework for fairness solicitation in an actual child welfare setting. So first, motivation. I think that algorithmic fairness is primarily a problem of stakeholder accountability, right? So companies and governments are accountable to stakeholders like consumers and citizens. And we've seen a million stories of companies or governments shutting down new technologies after public outrage over algorithmic biases, right? So for example, Amazon scrapped a recruiting algorithm after people found out that it was biased against women. Where I'm at in St. Paul, Minnesota, the county attorney's office scrapped an algorithm for predicting which kids were at risk of criminal system involvement after a group of teachers and parents and community advocates protested that the algorithm was biased against Black and Indigenous students. For better or for worse, I think that algorithmic fairness, as it's kind of currently conceived, is primarily about addressing and preventing these situations of stakeholder outrage. So I think it would make sense to involve stakeholders more in the process of designing these algorithms to be fair. And particularly, I think this is a kind of shift of the problem of defining algorithmic fairness away from an approach of solidifying some group-wise parity constraints based on simple moral principles into an approach of satisfying stakeholders' moral preferences about what is fair, right? And this argument aligns with philosopher Pak-Hang Wang, who suggests that the problem of defining algorithmic fairness ought not to be only a moral problem, but also a political problem, right? So to give an example, let's consider Twitter's snafu over their cropping algorithm, right? So Twitter used to have this algorithm that would crop large images down to just the part of the image that the algorithm thought was like the best part. And last year, a PhD student, Colin Madlin, found that the algorithm was racially biased. There were a bunch of people who tweeted out oversized images that included pictures of like a Black person and a white person. And regardless of the orientation of these images, the cropping algorithm would consistently crop out the Black person and crop in the white person, like we see in the two images in the middle here. So in response, Twitter did something that was actually quite interesting. Instead of just scrapping the entire algorithm, they opened up the model to the public and asked people to send them instances where they thought the algorithm was biased. Okay, so then with all these elicited instances of biases, then the main problem becomes how to use them to create a fair algorithm. In other words, an algorithm that satisfies the fairness preferences of these Twitter users who pointed out these biases. So next, I'll go through a few options for kind of ways to solve these problems based on prior work. So first, the first option we could do is like use some group fairness constraints. Now, again, to reiterate, the problem that we're considering is how to make an algorithm that satisfies stakeholders' elicited fairness preferences. So the kind of fairness constraints that we apply in our algorithm will depend on the instances of biases that people point out, right? So if all these elicited instances of biases are kind of these like Greg Jamal cases where we have similar pairs of images that differ only based on race, and that's all that stakeholders care about, then group fairness might actually work quite well here, right? We can imagine a classifier like the one on the right could be trained to satisfy demographic parity based on race and have like an equal cropping rate across Black and white people. But maybe this isn't really the case, right? So Twitter users' fairness preferences are unlikely to be relegated solely to race. Kyra Yee, the lead researcher on this project at Twitter, seems to agree. They say the discussion of race is basically just overly simplified to Black and white. And there's a bunch of other things that could potentially be going on. For example, there might be a bunch of elicited instances of bias based on gender. And then you would want to apply some group fairness constraints based on race and gender. But if you apply these group fairness constraints like independently across race and gender, then you run into this problem of subgroup fairness gerrymandering, where you can imagine a classifier like that on the right, which satisfies demographic parity based on race and gender separately, but always crops out Black women and always crops in white women, right? So stakeholders are likely to point out biases across multiple different kind of protected attributes at the same time. In this case, group fairness might not work. So instead, maybe a suitable alternative is subgroup fairness.
Logan?
Yeah, go ahead.
Just a question. Can you clarify what exactly is the information that's being elicited? Is it like a single example and a determination of whether that example is fair or unfair?
Yeah, exactly. So it'll be like a bunch of images like this, where you could have like a pair of images and it's oversized. And so you could imagine kind of like a binary classification on the image of this person versus this person, which one should be cropped in and which one should be cropped out. And then based on that classification, then some stakeholders would point out that like this classification is unfair.
I see. Okay, it's a bit, so like if I have two people, like image of, two people, then presumably we would want to crop the face of like one of them. So maybe both options are always unfair.
Yeah, maybe. I mean, you could imagine like, you would have like equal rates of cropping in or cropping out, like Black versus white people or something like this might satisfy some parity constraints based on race.
Yeah, so I guess I'll stop after this, but like maybe my concern is that like this really depends on the distribution of instances that people filed in. Like if I, chose to, yeah, I guess you mean like you understand what I mean, right?
Mm-hmm. Yeah, and I guess this is kind of part of the point as well, is like, okay, we want to satisfy these preferences, so eventually I'll say like the kind of distribution of the images that people point out are unfair is like what we want to get to eventually. And so maybe these like group fairness, or I'll say even maybe subgroup fairness, isn't like adequate for satisfying like the kind of distribution of classifications that they point out is like fair or unfair.
Okay, thank you.
Okay, sweet, thank you. Okay, so maybe an alternative like way to satisfy stakeholders' fairness preferences in this instance is subgroup fairness. And this is actually like closer to what Twitter saw from the kind of elicited instances of biases from stakeholders and from its own internal research, right? The algorithm was biased based on multiple different lines. So rather than just like race and gender, it's like biased against people with darker skin, lighter hair, more masculine features, more older features. So then we might want to mandate some parity constraint based on intersectionally defined like subgroups. And I can't plot like a classification rates in like 4 dimensions or whatever, but you can imagine that this little boxes on the right is like, 4-dimensional subgroups based on these 4 different characteristics, and that in each of those subgroups, you get like people who are older with darker skin and light hair and more masculine features, and older people with dark hair and light skin and feminine features have like equal classification rates, and so on and so forth, like defined based on these like 4-dimensional defined subgroups or whatever. So this might work actually quite well, right? Probably an algorithm that is subgroup fair in this sense is going to satisfy a lot of Twitter users like elicited instances of biases. So this algorithm would probably prevent a lot of these instances of biases from happening in the future. However, even really granularly defined subgroups may not take into account stronger fairness preferences about certain subgroups or specifically like individual cases. For example, this was one of the instances that went viral where a bunch of people thought it was really unfair to crop out Obama and to crop to Mitch McConnell, right? So a lot of people thought this specific classification was particularly unfair. We could also imagine that a lot of people thought this was particularly unfair because not only because Obama is Black and has darker skin and Mitch McConnell is white and has lighter skin, but also maybe because of the stature and importance of these two people, right? Obama's the president. And so this is like a particularly important example. In this case, like even group fairness and subgroup fairness may not be able to satisfy these kind of individual, particularly important constraints. So we can imagine a model that satisfies subgroup fairness or group fairness, like the one on the right, but that always crops out Obama and always crops in Mitch McConnell. So it seems like group fairness and subgroup fairness aren't really going to work to satisfy stakeholder preferences. Let's think of a different option here. So the different option, and these are much better options. First, from Yahav and Christopher and Stephen, we have like metric-free individual fairness in online learning, where they set up this online learning problem where each round you deploy a model, the classifier or the model classifies some pairs of samples, and then a fairness expert or judge says whether or not that classification is fair. And then they give some algorithm which achieves sublinear regret and limits the amount of unfairness that people point out over time. So this is pretty much like exactly the solution to the kind of problem I've posed so far. So feel free to leave this talk and go read their paper instead or something. But I think there's still like a little bit left to be desired here. And maybe we have to shift the problem very slightly. Namely, you still have to deploy a classifier and then basically get feedback from stakeholders after you deploy it about what's unfair. Where we can imagine a company like Twitter wouldn't want to essentially release a faulty algorithm into the wild so that people can just kind of, shit all over it and then, have a lot of PR backlash and stuff like this. Instead, we might want to ask stakeholders about their fairness preferences and train an algorithm to satisfy them and then deploy the model, right? So to this slightly modified problem, one solid related work that comes to mind is Cristina Ovento's work on metric learning for individual fairness. This work proposes to ask people about similar pairs of cases and how similar, how the distance between them, in order to learn some distance metric to be used in an individual fairness constraint, right? So this satisfies the problem above, where you can elicit these fairness notions before you deploy a classifier. But the problem here is that we still need some assumptions about consistency in order to fit stakeholders' fairness preferences in some metric. So then the fully modified problem, or whatever problem that we want to solve today, is okay, how do we elicit and then satisfy stakeholders' fairness preferences before deploying a classifier so that we can create an algorithm that satisfies those preferences without making like any assumptions on their preferences. Next, I'll discuss like how we set up a computational problem, but I want to pause for a second and make sure this is like clear to everybody. Okay, so if nobody has any questions, again, yeah, feel free to jump in with questions at any time. But like next, we're going to set up like a computational problem to how we solve this problem of eliciting fairness constraints. So first, we want to justify this approach of eliciting fairness preferences by asking about pairwise comparisons. So I want to argue that this is actually like a good way to capture some intuitive fairness beliefs. So for example, you could imagine like in the 2018 US Open women's finals, for anybody that plays tennis, an umpire gave Serena Williams like 3 penalties, one for accusing her of cheating, another for throwing a racket, and third for like arguing with the ump. And the last one, she was penalized like a whole game and $17,000. So a lot of people said that these penalties were like really unfair. In particular, another US tennis player, James Blake, tweeted afterward, right, "I have said worse and not gotten penalized, and the ump should have at least given her that courtesy." Okay, so mathematically, we can like represent these intuitive fairness beliefs by imagining that the ump is like a binary classifier H ump, which maps from a set of tennis players in certain situations to some binary classification where a positive classification is a good thing, no penalty, and negative is bad, penalty. So what Blake is saying then is that it's fair only if the classification for Williams is equal to or greater than that of himself in a similar situation, right? And that it's unfair that his fairness preference was violated when Williams was given a negative classification and when Blake would have gotten a positive one. So this seems like an easy way to ask people about their fairness beliefs and then take those like intuitive fairness beliefs and encode them so that we can define some computational problem. So in general, we can ask stakeholders these kinds of questions about their fairness beliefs by presenting them some pair of samples, A and B, and asking a stakeholder or a set of stakeholders whether A should be classified as well as or better than B, or vice versa, or should they be classified strictly equally, or no opinion, right? And then we use these questions in the following general framework. So first, we take a random sample of training data from some population. Here, the samples is like X2, X3, and X5. And then we produce every possible pair of these samples, and then we present those pairs to a stakeholder or a group of stakeholders and ask them the 4 questions above. Then, based on the responses, we translate those into these technical fairness constraints. So for example, if stakeholders all agree here that X2 should be classified equally to X3 and better than X5, and that X3 should be classified better than X5, then we get the following elicited fairness constraints. And these constraints can then be used to produce some set of like feasible classifiers, like the ones on the right here. And then the learning problem is reduced to finding the classifier within this set of feasible classifiers that minimizes classification error or loss. Now, this is an overview of the general framework. So before I state like the optimization problem that we're actually looking at, there's one like slight problem with these constraints. I think they're too strict. So it would be infeasible to like strictly satisfy all of these stakeholders' preferences simultaneously, especially if you have like a large group of stakeholders that disagree a whole bunch. There's probably going to be a lot of cases where if you want to strictly satisfy these constraints, then the only classifier that's going to be feasible is some constant classifier. So instead, we want to relax these constraints in order to set up like a reasonable computational problem. And we do so in two ways. Well, like really, I guess it's like three kind of relaxations. So the zeroth or whatever relaxation is that rather than trying to satisfy constraints over the realized labels, we look at the probabilities of positive classification between a pair of samples for some randomized classifier D. So, right, if a stakeholder thinks that sample xi should be treated as well as or better than xj, then in our like technical constraints, this means that the probability of positive classification for xi is greater than or equal to that of xj. Okay, and then we can add this first like relaxation gamma, which is the maximum pairwise fairness violation or the difference between xi and xj where some fairness constraint holds. So for example, if a stakeholder says that xi should be classified better than or equal to xj, then this ordered pair goes into this constraint set C, which means that the probability of positive classification for xi should be greater than that of xj. But then let's say like gamma is 0.1, this is like a little bit of wiggle room. So the difference between xi and xj can have this little wiggle room where we consider it to satisfy the stakeholders' fairness constraints if the probability of positive classification for xj is at most 0.1 or gamma greater than that of xi. So this is kind of like a L infinity relaxation over the fairness violation for each pair. The second relaxation, eta, is a kind of like L1 relaxation. So given gamma, each ij pair contributes some like excess fairness violation if the difference in probabilities of positive classification between xj and xi is even greater than gamma. In that case, we still want to like have a little bit of wiggle room for some fairness violations beyond gamma for each pair, but we don't want the sum of these excess fairness violations over all ij pairs in our constraint set to exceed eta. Okay, great. So with those relaxations, we can define our computational problem. So this is our fairness constrained empirical risk minimization problem where the fairness constraints hopefully satisfy some relaxed version of like elicited fairness preferences from stakeholders. Okay, so here it is with colorful labels. We want to find some randomized classifier that minimizes classification error subject to the following constraints. So first, that for any ij pair in our elicited fairness constraint set C, the gamma fairness violation, which is the amount that the probabilities of positive classification for xj exceeds that of xi beyond some amount gamma, is less than each like excess fairness violation slack variable alpha ij. So we put this alpha ij in here to go into the second constraint. So the second constraint is that the sum over all these excess fairness violation slack variables alpha, each weighted by the proportion of stakeholders who endorse the inequality like fairness constraints on a pair ij, does not exceed some total excess fairness violation amount eta. Okay, so that's a bit of a mouthful, but this is important. This is kind of like the first, I guess, contribution of our work here. So I'm going to pause here for a second if anybody has questions about this.
Yeah, so just like super quick question to make sure that I understand. So pretty much like what your alpha ij here is doing is like it's taking the maximum of that violation and 0, right? Pretty much. Okay,
Yeah.
thanks. Yeah.
Or you could imagine like it's like a budget for each
Right.
ij pair.
Yeah.
So I have like, it's not a technical question, but I am wondering, like, I know that there's a lot of work in machine learning on kind of either ranking or classifying from pairwise information, like when all you can ask is these types of pairwise queries. So like, I'm wondering how it's different. Like, is somehow the pairwise information when it's a fairness question, does that differ from like their standard formulations?
Yeah, this is a good question. Maybe something I'll touch on like later, or we can touch on later in QA2 or Q&A. Yeah, I think that like a lot of the pairwise fairness or pairwise like machine learning, whatever other works might apply here. Particularly, I think that like maybe we still want to satisfy. Yeah, I don't know.
Yeah, I
I'm trying
think
to think, yeah.
their objectives are sometimes a bit different, and
Yeah.
also sometimes they don't assume that you have labels at all. So also like trying to
Mhm.
minimize the error doesn't necessarily make sense. But there is some interesting work on like the formalizing this in the bandits setting where you can like pull a couple of arms, and then that means that you get like the information about the comparison. And like, I guess if you think about the arms as like, you know, responses to stakeholders preferences, then maybe like technically there is a connection there.
Yeah. No, I think that's a good question and something I should probably think more about.
One
yeah.
thing I might
Well,
just
well,
jump in
well,
and
stop.
say,
Yeah, yeah.
I think so first of all, there's not some huge technical obstacle here. Like the pairwise constraints are just represented as like linear constraints, and I wouldn't be surprised if, you know, people have written down linear programs before. But distinct from these, or at least the sort of typical ranking problems I'm aware of, here these are the constraints rather than the objective. So the objective is still the standard thing, you know, minimize error, and then there are constraints that come from these listed things. But we're sort of doing the obvious thing here, which is to introduce a linear constraint every time someone tells us to.
I've put a question in the chat.
Let me see. No, yeah. So there's
Okay,
no
thanks.
consistency assumptions on even single judges. Yeah. Cool. And this is kind of like one of the nice things about this work as well, motivation as well, is that, okay, how do we do this, satisfy preferences without making any assumptions about even single judges? Okay, so if there's no other questions, I'm going to do a slight recap. Okay, so we started with wanting to create an algorithm that satisfies stakeholders' fairness beliefs. We elicit those beliefs by asking them to compare pairs of samples and say, like a priori, how they should be classified to be fair. And now we use those responses to define an empirical risk minimization problem with constraints that should satisfy like a slight relaxation of those stakeholders' fairness preferences. And now I'm going to show how to solve this ERM problem. So first we define some Lagrangian, right? You can see the two constraints from the ERM problem with Lagrange multipliers here. The first constraint with this lambda, and then the second with tau. And we translate the constrained ERM problem into a two-player min-max game. Let me check the chat. Okay, never mind. Okay, so we translate the constraint problem into a two-player min-max game. So each round, the primal player plays some randomized classifier D and fairness slack variable vector alpha in order to minimize this Lagrangian. And the dual player plays some penalty weights lambda and tau to maximize it. And what I mean there is that, like for any IJ pair in our elicited fairness constraint set C, if the gamma excess fairness violation exceeds the primal player's slack variable alpha IJ, then this fairness constraint is violated. And the dual player can just like throw all its weight onto lambda IJ and blow up the Lagrangian. And also for that second fairness constraint, if the sum of those weighted excess fairness violations exceeds eta, then this constraint is violated, and the dual player can just like throw all its weight on tau and blow up the Lagrangian again. So next is to find a solution for this min-max problem. We actually want to find a solution to the max-min problem. So the dual player plays first and the primal player plays second. The solution should be equivalent, and so long as we play some no regret dynamics, and the solution to this max-min game should be like a solution to the original fairness constrained optimization problem that we showed earlier. And so by no regret, again, yeah, I mean the average regret of the difference in the utility that we get from playing our algorithm, and the single best play in hindsight converges to 0 with increasing rounds. And for no regret dynamics, I mean the following. So first, the dual player plays and wants to distribute these like penalty weights in such a way that anticipates the primal player's play, and then will penalize any fairness constraint violations as much as possible. Because these constraints are linear and the predictor H, the dual player can then solve for these penalty variables separately. So we run 2 no regret algorithms, exponentiated gradient descent to solve for lambda, and then online gradient descent to solve for tau. And then for the primal player, since the dual player has already played, they just need to best respond. And this best response problem is like a cost-sensitive classification problem, where the weighted error for playing some randomized classifier D is a combination of the classification error over the sample set S and the weighted fairness violations, weighted by these like dual variables, lambda and tau. So then with those cost-sensitive classification problems, we use some CSV oracle to get the randomized classifier D and then the slack variables alpha. Okay, so this is the no regret dynamics. I can then present our like main empirical result. So we prove that no regret dynamics I just described approximately solves the elicited fairness constrained ERM problem that I described earlier in an oracle efficient manner, meaning that the algorithm is polynomial time given access to some cost sensitive classification oracle, which we call when the best player, the primal player best responds. And so below is like the main theorem, which describes how accurate an approximate solution we can produce in terms of both the classification error, as well as like how well we satisfy the elicited fairness constraints, given some polynomial number of cost-sensitive classification oracle calls. So again, I'm going to pause here and recap. Like, this is great. We propose some simple approach to eliciting intuitive fairness beliefs. We set up some computational problem. Then we describe this efficient algorithm that we can use to solve this computational problem. And finally, we give some guarantees about how good of a solution we can get to that problem with this algorithm. Now, the only thing I'm going to go over quickly left is like a little generalization, and then I'll describe some application of this framework in an actual scenario. So for generalization, we have some guarantees for out-of-sample accuracy and fairness loss as well. The accuracy generalization is fairly straightforward. We just appealed to like the VC dimension method of bounding the error generalization through uniform convergent bounds, right? And then we also show like some fairness guarantees or fairness loss generalizes. So specifically, we show that the probability that the average fairness violation beyond gamma over all pairs in any sample set S drawn from the population is that is greater than alpha. That probability is small. There's a few little bumps in how to prove this, so we can't appeal to like the VC dimension techniques like we did with the accuracy generalization. But for the sake of time, I'm not going to go too much into it here. If you're interested, please feel free to check out the full paper for details. Suffice to say that like we give a high probability generalization guarantees for both error and fairness. So let's check out application of our framework in actual domain. This is actually a second paper that followed the elicitation techniques of the first paper I just presented. This second paper is titled Soliciting Stakeholders' Fairness Notions in Child Maltreatment, Predictive Systems. This is a joint work with a different set of co-authors, Sans, myself, and Stephen. So here we have Haofei Cheng, Ruchi Wang, Paige Bullock, Alexandra Sholdashova, and Hai Zhu. This paper is about eliciting fairness beliefs in the way that I described earlier from stakeholders in the context of the US child welfare system. So we interviewed 12 people, 8 social workers and 4 parents. I should say, if you're unfamiliar with like child welfare, okay, if you make a report, it's like calling 911, except it's usually not an emergency. So there's child welfare workers that will listen to the reporter. Usually the reporter is like a teacher or relative, and then the child welfare workers will look up a bunch of information on the people reported in the case, the adults and children. And this is like everything that the county or city or government has on those people. And then based on the report and this additional information, a caseworker will decide whether or not to investigate this family. And this like decision-making scenario is increasingly being augmented by machine learning-based recommender systems. So this is like a real classification setting. Okay, so again, so we gave 12 interviews. During each interview, we showed each participant 14 pairs of reports of child abuse or neglect. These are synthetic reports, we made them up. So we included like 17 features. In a real report, you might see hundreds of features and additional writing that can't be captured by features. But our fake reports included similar information to the real reports, like demographics, current information about the current allegation, past child welfare reports made about the family, et cetera, et cetera. And then each study participant then had to compare each pair of cases and decide whether one report should be prioritized for investigation over another in order for this classification to be fair. Right, so here we also made some like graphical interfaces for participants to explore the cases and compare them with one another. Here's one of the interfaces. So you can look at each of the cases, read through, like, here's all the features, here's the report, and then compare these two to one another. And then select some options that are essentially the same kind of questions that I laid out earlier in the general fairness elicitation framework, where, okay, should case A be prioritized over case B? Should B be prioritized over case A? Should they be prioritized strictly equally, or no opinion, or whatever? So the results that we got from this study are kind of a mixed bag. For one, the pairwise fairness like constraint, the pairwise comparisons to make these fairness constraints were like really intuitive. So this was good. People didn't have any trouble answering them. They seemed to align with people's like intuitive fairness beliefs. So this is a good way to capture like people's fairness preferences. However, those preferences like differed quite a bit. Stakeholders didn't really unanimously agree on many pairs of cases. Some cases, they were completely split between responses. There were, I think, 1 or 2 where there was like near unanimous agreement. And this is significant because disagreement leads to poorer algorithmic performance, right? If you have like a lot of disagreement, you're going to have a more constrained set of classifiers that can satisfy those fairness constraints. And then that leads to worse performance. This isn't just specifically to our paper. This is like the other papers that I mentioned previously that also do this like fairness elicitation. This is also a problem in their works that they mentioned, like disagreement. So this one limitation leads to some future work maybe for these kind of fairness elicitation techniques. One, you could try out different ways of eliciting to kind of encourage agreement. So for example, you could just ask people in a group and then have a kind of group deliberation, like jury deliberation, ask the people, maybe come to a consensus about their preferences. Two, we could circumvent these disagreement entirely by applying like some voting methods or social choice methods where, right, again, so that these fairness preferences are essentially just like a partially ordered set ranking over all the samples in your training set. So maybe like social choice methods would work very well here. I have some thoughts on that later if anybody's interested. And lastly, like in some of the interviews with stakeholders, a lot of people weren't really concerned with algorithmic fairness, as in similarity constraints between individuals or groups of people. A lot were more concerned with like whether using these ML-based technologies in certain contexts like child welfare or the criminal system was fair in the first place. So it might be worthwhile to expand moral considerations of fairness solicitation beyond what we would usually consider like algorithmic fairness. Okay, so that's my talk. Thank you all for listening. And again, thank you to my wonderful co-authors. Again, my name is Logan Stapleton. There's my email. And I guess we'll open up for questions.
Yeah, thanks a lot, Logan. So yeah, if anyone has any questions, now's the time.
I think my question is a little outside of the scope, so I think it's fine to not answer it. But when I was thinking about your motivating example in the beginning about, like, if my model is randomized and like maybe 10% of the time it crops like group B, but 90% of the time it crops the majority group, and I'm only assessing whether there's a fairness violation from looking at one output. Like, do you have a sense of fairness situations where like determining a violation actually does require looking at like multiple examples? Like maybe I do need to look at the cohort. And so that's kind of my basic question. Like, can you go from the group, from pairwise to the group maybe, or like, anyway, so that's my question. Really enjoyed the talk.
Yeah, so if I'm understanding right, I think maybe there's two kind of concerns here. One is that like on the realized labels, maybe people would look at one example and think, oh, this is unfair. How do they know that like the algorithm is fair in general if you have some probabilistic classifier? Is that right?
Maybe more concerned people think it's fair just on one realization, and so then you don't detect fairness violations.
I see. Yeah, I don't know. Yeah, this is like a good point. I think that this is part of the point of like relaxing these fairness constraints is like not exactly satisfying their fairness preferences, but hopefully we can get close, and hopefully people will point out like realized examples that generally match like unfairness that they see in the algorithm overall. That's what I would think, but I don't know. What do you like? Is that satisfying?
I think so, maybe. I think kind of what I'm thinking about here is something kind of like almost like redlining, where like when someone shows you one house and they say the valuation, there's like an ostensibly reasonable answer for that, but like detecting the violation, you kind of do have to look at the cohort maybe.
Yeah.
Really good.
I think that's getting at sort of maybe a more fundamental point that maybe is sort of worth discussion in this group, which is that in our community we often conceptualize fairness constraints as applying to randomized classifiers for various reasons. Like thinking about constraints on randomized classifiers is both mathematically and in some ways conceptually a little easier to think about. But I think probably if you're going to go out and ask people what they think is fair and unfair, they're going to tell you things about realized outcomes. And here's a concrete, I think, almost technical problem that was sort of one of the things we had in mind when we started this project, but is a little different than the problem we actually solve in this project, and I think would be an interesting technical problem to solve that might map onto sort of preferences over realized outcomes better. Right, so suppose people actually have preferences over realized outcomes. So, you know, what they think is unfair is sending someone to jail, you know, sending person A to jail and not sending person B to jail, and they don't care that it was a coin flip for each one. People have whatever fairness conceptions they want, maybe of this form, you know, like if A goes to jail, B should as well, or vice versa, or they don't care. But otherwise they can be arbitrary, and you're going to start making decisions, and they are going to start complaining and causing a scene when you do things that they don't like. In principle, there is still a well-defined trade-off here, right? Even if you have like a bunch of judges who are unrelated to one another, on the one hand, you can try to maximize accuracy on the data you have. On the other hand, you can try to minimize the frequency with which someone complains about what you've done. Right? In principle, there's a well-defined trade-off curve here. And the question is, can you give an algorithm for navigating this trade-off curve? Where the difference between like technically what we're doing here and in the problem I'm describing is people will complain based on realized outcomes. So even if you know, if I think A and B should be treated the same, and
So Aaron, you've been very concerned about this the fact that ex ante fairness doesn't give you ex post fairness for a while. Like we've had this discussion multiple times, and it's a valid worry. I've gotten to the point though where I'm pretty sure that if you ask, you present to an individual the same comparison on multiple occasions, they will not be consistent in their own answers on the same pair of people. And I'm going to bet real money that we can find instances of this, in which case the problem of being happy ex post seems unsolvable. So I'm not saying that the issue doesn't exist. I'm saying I don't understand what the boundaries are of what we could possibly hope for when we're talking about people's emotional responses to things.
I mean, I guess separately from modeling how people behave or thinking how they maybe should behave, there's still this very practical question. If you are deploying some tool, to on the one hand want to have your tool work well, and on the other hand want to sort of minimize like criticism based on whatever considerations, fairness or not. And however you model people's behaving, at least if you model them as reacting to what they see, which is the outcomes rather than the sort of probabilities, in principle, you can navigate this trade-off, right? Like you can maximize accuracy among all of the models that cause someone to, you know, that cause the level of complaint to like rise above some threshold only 1% of the time. And I guess I'm just saying that might be an interesting question. You could motivate that question a number of ways. One of which would be sort of imagining that people really do care about realizations, but another one is just the purely sort of practical consideration of wanting to sort of do well subject to the constraint that nobody is too unhappy.
So you may well be right, but once we're getting into, you know, being unhappy or how unhappy or too unhappy, we're into this thing that has, I'm not even sure how you measure it. And I don't know what proxy we'll put in for measuring it. I don't know that the self-reports, yeah, lots of questions. It's a little bit like saying, does somebody understand something? You know, who the hell knows what their answer means?
Yeah. The only thing is, I guess when posing the practical version of the question, I'm trying to avoid hard questions of, you know, do they understand things and why they are complaining, and just sort of taking the fact that, taking as given that, you know, they are complaining according to some, you know, some rule, possibly, you know, possibly non-deterministic, and wanting to minimize the degree to which they complain.
So yeah, by the way, I think Omer also wants to say something. He's been raising his hand for a while now.
Sorry.
No, it was an interesting discussion. I was waiting and listening. Let me raise something about the kind of the example with the Twitter cropping. That in a sense, when Twitter gets that and then goes into this public thing, and it feels to me like trying to manipulate their users to feel that they are fair, or it feels more like a PR thing. And I feel that there is a worry that if you are trying to, but companies are very good in manipulating. So I fear that we should distinguish trying to elicit opinions from policymakers and preferences and trying to communicate with them, and something like we're trying to make our users think that we are fair, which is kind of trying to manipulate our users to feel that we are fair. So there is some line there that I need to, that I I'm not completely, I don't have a very clear opinion of, but that needs some concern.
Yeah, the Twitter bounty program was silly for a large number of reasons, I think.
Can you say more, Aaron? Why do you think so?
Oh, so here are the reasons, I guess. I think that it was mostly a PR stunt. So first of all, this cropping algorithm that they opened the bounty program up for is something they had already stopped using. So this was not a bounty for like a piece of code that Twitter was actually using, let alone something related to how they make money, right? Like they should really do a bounty program for like their news feed algorithm or something. So they'd already stopped using this and just have let people crop by hand. Second, they only like it was a one-off thing that was launched with only a week's notice, and so like I don't think had the possibility that anyone would be able to spend enough time to uncover serious things. Maybe I'll stop there. I think those are the. But I do think that a bias bounty program is a good idea in general.
Well, it's more than like their competitors have done, so I guess they deserve that.
I'm not sure I buy it.
Okay, that's
I mean, each company has its own way of manipulating the public.
What I will like a real bias, like a real security bounty program. Like the whole point is to open up to scrutiny actual crucial parts of the company's software so that they can learn about the problems ahead of time and fix them. So I will be impressed when someone launches a bounty program that is actually exposing to scrutiny something that is used and related to the bottom line of the company.
Right. But I also want to say that it's not a majority kind of thing. So something can be very unfair, but the majority will still be very happy with it. And so there is something to think about.
I also think that a lot of the responses were like, you shouldn't be using this cropping algorithm, just let the people, uploading the photo determine the cropping. It kind of relates to what Logan said in the end about, maybe the thing we're eliciting shouldn't just be the preference. It should be like, whether we should be doing this specific task at all.
Aaron, I was just thinking about this is not a company-run bounty program, but for financial companies, the SEC will award whistleblowers money proportional to like, if you whistleblow on a company and then they're assessed like a fine, you're given a percentage of the fine. So anyway, I kind of wonder if there's some discussion about the effectiveness of that type of program.
Mhm. Right, I also read about that recently in the context of the Facebook whistleblower.
Yeah, that's why I was thinking about it. It seems like interesting. I'm excited. I'm interested to see how that will continue to develop.
Cool. Does anybody have any questions about the work or anything else? Or otherwise, I can probably stop sharing my screen.
I mean, I guess we're on the we're on the hour right now, so we should probably stop here. But yeah, thanks again, Logan, for the really good talk. It's really
Thank
nice.
you. Yeah. Thank you so much. And thank you for the